Thank you guys for coming to my talk. So in contrast to the previous talk, which was about algorithms for quantum max cut, in this paper we'll be talking about moving towards a theory of hardness of approximation for quantum constraint satisfaction problems. This is based on joint work with Joe Neeman, Ojas Parekh, Kevin Thompson, and John Wright. So at a high level, what we're trying to study here is developing a theory of hardness of approximation for quantum CSPs. And really, before we talk about that, I want to try to revisit a little bit about the theory of classical hardness, because this will do a good job at setting the stage and give us a sense of what we are able to show and what remains to be shown. Then I'll give an overview of our results, which include an integrality gap or a optimality result for algorithms using semi-definite programming, and then the first quantum hardness of approximation result. Then I'll discuss something called Borell's inequality, which is really key to a lot of these classical hardness results, as well as ours. And then I'll conclude with some open questions. So first, let's start with the point zero. So most of you have probably seen this problem before, but classical max cut is very important for setting hardness of approximation, at least classically. So this is a problem on a graph with vertices and edges, and the goal is to find some function which maximizes the number of edges which are cut. In this example, if we color the edges like this, then the edges that are cut correspond to those edges whose vertices are assigned opposite labels. So in this example, this edge is cut, and in particular, these red edges are cut in this graph. Then, of course, to compute the number of edges that are cut, we can take the sum over this indicator that for each edge, the function assigns a different value to each of these endpoints. And the objective, of course, is to maximize this over all f. Now, we'll be a little bit more formal and replace yellow with +1 and blue with -1. And then our indicator takes this specific form, where you can see that this inner term is -1 if the edges are different. So this overall term gets 1 if they're different and 0 otherwise. So this is just max cut, as we all know. Max cut is a quite interesting problem. It's NP-hard, and you could really view it as a very quintessential NP-hard problem, partly because its constraints are very simple. On each edge, you're just checking equality between the assignments for each of the vertices. And as a result, it's been really central in developing the theory of approximation algorithms for NP-complete problems, as well as studying hardness of approximation. So because it's NP, we can't design exact polynomial time algorithms, so we often study approximation algorithms. And really, the most simple thing you can do is go to each of the vertices and just assign a color uniformly at random, either blue or yellow. And this gets a value of 1/2. And by 1/2, what I mean is that this algorithm for max cut, gets value at least half of the optimal value. There was a series of works that slowly improved on this, but these all really stay within the 1/2 regime, right? They don't do asymptotically better than the naive random algorithm. And the first result that really broke free of this was the algorithm of Gomez and Williamson, who showed that by using semi-definite programming, you can actually get a ratio of 0.878. And this is kind of remarkable, and it really makes you wonder, like, how far can we take this? Is it possible that although getting a 1 approximation is NP-hard, is it possible we could get like arbitrarily close, maybe like 1 minus a very, very small constant? Well, this was exactly answered by KKMO in 2007, who showed that doing any better than this Gomez and Williamson ratio is actually NP-hard, assuming the unique games conjecture. This proof uses Borell's inequality, and this is something that will show up again later in the talk. So this is exactly the region that's blocked out by KKMO. And really, this situation is not unique to max cut. It's kind of remarkable, and it was something that the previous presenters remarked on. But it turns out that Gomez and Williamson, they use this semi-definite programming algorithm, and you can actually generalize their algorithm to develop this notion of a canonical SDP, or like a basic SDP. And Ragaventure showed in 2008 that actually for every classical CSP, this canonical SDP gives you the optimal classical algorithm for these approximations. It's kind of crazy, and like we have a very firm understanding of what classical approximation looks like. Unfortunately, no such theory exists for quantum optimization, and we don't really have a sense of what the right choice of algorithms are. So with that, let me move into quantum CSPs. And to do that, let me rephrase max cut in a more quantum language. I apologize for those who are very familiar with this area already. So we have this constraint graph, and let's look at this edge UV. Classically, what we're doing is we're looking at this binary string and trying to and associating this with an assignment to U and V. So this corresponds to an assignment for U, and this corresponds to an assignment for V. And then we check on this edge whether S of U is not equal to S of V. Well, we're going to be talking about a quantum problem, so let's generalize this to quantum states. And what that really means is we're going to replace S with a quantum state psi. And now, since we're still talking about classical max cut, we want to restrict ourselves to classical measurements. What this looks like is that we want to treat psi like a classical string and only allow z basis or standard basis measurements. So we look at the qubit corresponding to u, measure in the z basis to get either +1 or -1, and similarly for the qubit corresponding to v. And now if we let zu be this operator which performs this measurement, let's rewrite this constraint as saying not only is s sub u not equal to s sub v, but zu when applied to psi is not equal to zv applied to psi. This yields a Hermitian matrix, which will end up being the constraints of our quantum problem. And in particular, it takes this form, h sub max cut equal to 1/2 identity minus poly z tensor poly z. Now, how do we generalize this to the quantum world? Well, in that regime, we not only have access to z-basis measurements, but we can also make x and y-basis measurements. So we not only perform the z measurement and check whether they're unequal, but we also make this x and y-basis measurement and check equality in those as well. This x basis is also known as this Hadamard basis. This allows us to extend the Hermitian matrix from the previous slide to this h sub q max cut constraint, where we also check, where we add these x tensor x and y tensor y constraints. So it's almost like we're solving 3 instances of max cut simultaneously. And of course, this is not just a single constraint, but it's going to be part of a larger constraint graph. And we have some state psi that acts as an assignment to all of these qubits or vertices. Much like max cut is an instance of a CSP, quantum max cut is an instance of a more general local Hamiltonian problem. And in that case, we associate general Hamiltonian constraints, which are Hermitian matrices, h sub uv to each edge, and we measure the degree to which a state satisfies this constraint by taking the left and right product with respect to this matrix. And this is also called the energy. The total energy of this assignment is given by summing over all of these constraints to get this following form. If you look at this, then you can observe that psi is a norm one vector, and thus this is really the maximum eigenvalue problem for this matrix. So why do we care about quantum max cut? Well, this was mentioned in the previous talk as well, but really, we shouldn't just take classical problems and convert them into quantum problems. There should be some reason why we care about these problems. And one reason is that it's a very physically motivated problem. In particular, it models a magnetic system on particles with opposite spins, and it's been extensively studied in physics literature under the name of the antiferromagnetic Heisenberg model. Not only that, but much like max cut is NP hard, we know that quantum max cut is actually QMA complete, where QMA is the quantum analog of NP. And thus, the hope is that, much like max cut has really improved our understanding of approximation and hardness for NP, quantum max cut helps us make similar progress in the world of QMA and quantum. A couple of disclaimers. We talk about maximization here rather than minimization, whereas local Hamiltonian is usually phrased as a minimization problem where you try to compute the smallest energy. But in the end, it's QMA hard in the maximization and minimization world, so it doesn't make too much of a difference. Additionally, we talk about locality in terms of the number of qubits, whereas in physics literature, locality usually refers to nearby neighbor interactions. So it's a bit different in terms of terminology. So where do we stand in terms of approximation? Well, the algorithm that we'll really care about for this talk is based off of the work of Gribby and Parekh in 2019, who showed that by using a generalization of the canonical SDP that I mentioned earlier, you can actually get a ratio of 0.498. This is kind of cool, and it has a lot of similarities with the classical algorithm. And as a result, let me spend a couple slides trying to compare these two algorithms with each other. So the Gomez and Williamson algorithm, what does it do? Well, we're solving max cut, so we want to assign +1 or -1 to each of the vertices. This corresponds to putting maybe V3 at the -1 point on the x-axis, and V1 and V2 on the +1 points. Then in semi-definite programming, what we want to do is actually relax this assignment. So rather than solving a discrete problem, we allow these points to take vector assignments. This is notation for the n-dimensional unit sphere. This looks like moving V3 to this point and moving V1 and V2 to these points. So now we have vector assignments, not just discrete assignments. And rather than solving this optimization problem where we have this product of f of u and f of v, we now look at the inner product between these vectors. Finally, what Gomez and Williamson do to convert this vector assignment back into an integral solution is that they pick a random hyperplane and they assign every vector on one half of the hyperplane +1 and everything on the other side -1. Now, how do we generalize this to the quantum world? Well, what the algorithm of Gurry and Parekh do is that we are now not looking for a +1 -1 assignment because we're talking about qubits and quantum states. Instead, we look at a single qubit state, which can be represented in its block sphere representation. So this is just a way to write a single qubit state where each of these x, y, and z's are the Pauli matrices. Then, if we look at these coefficients attached to each of these matrices, they actually correspond to a 3-dimensional unit vector, which we call a block sphere vector or block vector. Then, much like in the previous algorithm, what we do is relax this into the n-dimensional sphere and associate these vectors with each of these points. Finally, we do something very similar to Gomez and Williamson, and we now pick a three-dimensional hyperplane rather than just a one-dimensional hyperplane, and we project each of these vectors onto this hyperplane to get back a block sphere representation. If you note, this algorithm really only cares about these states on single qubits, so the final state that we output is actually a product state formed by taking the tensor product of each of these individual states. So what can we do beyond Gruby and Parekh? Well, there might be some classical intuition that due to the results of like Raghavendra and KKMO, maybe like the best thing we can do classically for solving quantum max cut is this canonical SDP. But it turns out this intuition actually does not hold. And in fact, the result by Anshu Gosset-Morenz in 2020 actually showed that you can do better, getting a ratio of 0.53. This was followed up by several other algorithms, Parekh Thompson in 2021, and then the results of Lee and Robbie King that you just saw. So again, you might ask yourselves, like, how far can we take this? How far can we take these approximation algorithms? And to partially answer this question, let me move into an overview of our results. So the first question that we really ask is whether SCPs are still the right choice for quantum max cut, just because that we saw that like SCPs somehow fail in this very like powerful way, that this canonical SDP that has always sufficed classically just isn't the best anymore. To partially answer this question, our first theorem states that there exists an instance I such that any algorithm which uses this basic canonical SDP gets at most a 0.498 approximation. So if you restrict yourself to the canonical SDP or the level 1 of the Lasserre hierarchy, you can't do better than the Grubian and Parekh algorithm. However, this does leave open the possibility that by going to higher levels, much like what Lee and Robbie King did, there is a possibility of designing a classically optimal algorithm. This result assumes our conjectured vector value Borell's inequality, which I'll try to justify later on in the presentation. The second theorem is about developing a more robust theory of approximation, which applies not to just to STPs, but just to any classical algorithm. In that regard, we are able to show that doing any better than a 0.956 approximation is NP hard, assuming unique games. And this should really be viewed as an analog of the result of KKMO. But in that case, they were able to exactly match the Gomez and Williamson algorithm. But as you might notice, there's a significant gap between our approximation ratio that we have shown to be hard and the best possible. And again, this assumes our conjectured vector value Borell's inequality. Sorry for the formatting. So where do we stand in this approximation picture? Well, the first result, theorem 1, states that you can't do any better than this algorithm of Gruby and Parekh. On the other hand, our hardness result is all the way here on the right, and we show that you can't do any better than 0.956 for any algorithm, any classical algorithm. So really, there's a huge gap between the best possible algorithms by King and Lee and our hardness result. A natural open question, of course, here is to bridge the gap between these two. So finally, let me conclude by trying to discuss a little bit about Borell's inequality. This is a very key result in the classical results, and the first result of KKMO actually was conditional on this conjecture that they call majority stabilist. And it turns out, at the heart of this conjecture was Borell's inequality. And in fact, Mossel, O'Donnell, and Oleshkovitz showed in 2010 that by using Borell's inequality, they're able to resolve the majority stabilist conjecture and fully prove the result of KKMO. Because our work should really be viewed as somewhat of an extension of the result of KKMO, we need some notion of a vector value Borell's inequality. And we give as one of the contributions of our work a precise statement of what such an inequality should look like. So what is this mysterious inequality? Well, it's really a statement about a geometric problem. Imagine you're working in Rn, and you start picking negatively correlated Gaussians. So points UV, and this might be a few of these negatively correlated Gaussians. Then what we do is we find a function which assigns a value to each point in the space. And this might be an example of such an assignment. And the goal is for each of these pairs, look at the assignments f of u and f of v. And we want to minimize the probability that these points get the same value. In particular, you can also write this as minimizing the expectation of the product. What Borell's inequality tells us is that not just any assignment will do, but in fact the best possible assignment which minimizes this expectation is the one where you take a hyperplane and you assign everything on this one side of the hyperplane +1 and everything on the other side -1. This picture looks really similar to the picture that we saw earlier when we were discussing STPs, and that's not a coincidence or anything. More precisely, what Borell's inequality tells us is that to minimize this expectation, the best thing you can do is look at the sign of the first coordinate of x and just assign based off that. And this is up to, you can choose any other hyperplane as well, not just the y-axis. So now how do we extend this to the vector world? Well, we start with the same setup, but rather than mapping to +1, -1, of course, we'll map into the k-dimensional unit sphere. So this might look like, an assignment might look like this. And now what we do is look at this pair and minimize the inner product between these two vectors. What our conjecture states is that the best possible assignment, given these constraints, is the one which follows these radially, these guidelines which come radially from the center. In particular, it might look like this blue assignment. More formally, our conjecture states that this inner product is minimized by taking the first k coordinates of x and normalizing. You might note that if you set k equal to 1, then you exactly recover the scalar valued Borell's inequality. So what goes wrong here? Like, what are some intuition we can provide in which shows that this inequality might be a reasonable one to make, or this conjecture might be a reasonable one? Well, one thing is that we are able to actually show this special case when we're going from the k-dimensional sphere to the k-dimensional sphere. And this uses Fourier analysis over an appropriate choice of basis. This is a non-trivial proof, but unfortunately, this doesn't suffice by itself. And the goal is to reduce this case from the full problem. What we try to do is we apply a dimensionality reduction, which initially starts from the n-dimensional sphere and reduces down to the k-dimensional sphere. However, this proof actually doesn't go through in the fullest, and in particular, it only works when we're dealing with positively correlated values UV, whereas I mentioned earlier that we really care about this negative correlation case. So what's next? Well, one thing is that we should try to show this inequality. Our proof attempt of this actually takes up the majority of our paper, and we're able to show it in a very special case, but the question is, can we show the full version? It seems like some different techniques might be required just because of this issue with this negative versus positive correlation. On the other hand, a natural question is to ask whether we can bridge the gap between the best possible approximation algorithms, which either get 0.562 or 0.582 for triangle-free graphs, and the hardness result obtained in our paper. Second, we should really try to study the strengthened hierarchy of SDPs and come up with maybe optimality results for those. Because as we saw earlier, you can do better than the basic SDP by looking at higher levels of the Lasserre hierarchy. Finally, in the end, we're trying to solve a quantum problem, quantum max cut. So the natural question to ask is whether by studying quantum algorithms, we can develop more sophisticated algorithms. Great. Thank you.
That's nothing. Okay. Oh, wow. We're going at a good clip, so plenty of time for questions.
Hi, thanks for your talk. So I was wondering, you motivated thinking about quantum max cut by like studying Heisenberg antiferromagnets in physics. Have you but you know, physical systems usually have geometric structure rather than like having generic graphs. Have you thought about trying to prove something about hardness for graphs that have some notion of geometry and that might appear in the
yeah, I think if you're looking at very structured graphs, then the problem becomes easy to compute. Like I think you can solve those in either BQP or even in polynomial time, depending on the type of graphs that you're looking at. I think like in particular for like things like lattices, and you have things like the area law that tells you that it's actually pretty easy to find a good approximation to the ground state. So really for these like MP hardness and QMA hardness results, then you really have to look at these very general families of graphs.
Okay, thank you.
All right, more questions? There's one over here.
Yes, thanks. Very nice talk. Yeah, so I have a question about your hardness. So you said given the unique gain conjecture, you can prove the 0.956 approximation factor is the NP-hard problem. So I'm wondering, do we know any, I mean, because it's sort of a quantum problem, right? So I'm wondering, do we know anything about the approximation factor for the QM complete? Say how large the approximation factor should be will make this problem still a QMA complete problem.
Yeah, so are you asking for quantum algorithms or for classical algorithms?
Quantum algorithms.
Quantum algorithms, I guess that's kind of asking, I guess, whether like BQP is equal to QMA in some sense, and that's, I guess, intimately related to like this quantum PCP conjecture, right? Like, 'cause if we know that there is a constant factor in which approximating quantum max cut is still QMA hard, then that will, I guess, resolve like quantum PCP. So I don't think we know any constant factor hardness results in the quantum for quantum algorithms, but yeah.
Yeah, I see. Thanks.
All right, I saw an arm over there.
Assuming the conjecture is true and the result is true, do you have any ideas how to bring down the upper bound?
That's a good question. It's hard to say. The construction that we have feels very natural in some sense, because in both this and in the result of KKMO, essentially what you're doing is you're looking at like this Gaussian ball, and you're comparing the value that these assignments get on the Gaussian ball and like the value you can get by looking at these like single qubit states or like these three-dimensional vectors. And for those, like the results seem very tight, right? At least when you look at these like very extremal examples. So to me, I feel like you need very different ideas if you want to try to lower this hardness result at all. But I haven't spent too much time thinking about how to bring down the value. I've been, this just showing this inequality by itself has occupied a lot of time. So maybe once that's done, then I can move on to improving the upper bound.
All right, thanks.
All right, more questions?
Thanks. Hello. Very nice talk. So quick question. The MP hardness result, right? That's not for a product state ansatz, right? That's like in general, it's just MP hard to approximate.
Yes. This is for product and for general quantum states.
Great. So how do you do that?
Yeah, the answer is actually quite simple. We essentially use a result that shows, sorry, I'm completely blanking on the authors, but it's essentially known that if you look at like higher and higher degree graphs, then you get, for very high degree graphs, then the best product state matches the performance up to a small factor of like the best general quantum state. So just because the instances that we're showing hardness for are these very high degree graphs, then you can't do better than a product state in the first place.
More questions? There, very good.
I have a comment on the previous answer and then a question which are unrelated. So the comment is that like for the 2D Heisenberg model is known to be QMA hard even on a 2D square lattice. If you have the weighted version or if you have the unweighted version but with local field terms, so additional local terms. And it's yeah, but I think but it's not known to be easy without, I think it's just an open problem. And so rather than it being easy because of area law, it's a unknown, and please go and solve it because it's not solved yet. But my question was, so you proved this bound based on using MP hardness? Oh, you got this MP hardness thing because you went to instances that were like you just said were very high degree, and then you get this good approximation. I would have sort of naively anticipated you'd have a barrier from QMA hardness.
I'm not sure what you mean. What do you mean by that?
Or other complexity. I mean, you've kind of got a bound on the hardness of approximation of a quantum problem where your limit is based on like going a better approximation ratio would prove MP is that bound is based on kind of getting to MP hard instances. But since we know there are instances of this that are QMA hard, can you improve the bound by using different complexity classes?
I see. I haven't really thought about how you would modify these results to show like a ratio at which it is QMA hard. But yeah, I guess that's an interesting line to pursue. Yeah, these results are very interesting because you're looking at these these graphs in which like you can almost use like a polynomial time algorithm to compute the max value. So yeah, it does seem like there should be more to be said if you look at QMA hard instances rather than MP hard instances. Thank you.
All right. Is there one more quick, maybe? No, then we're going to wrap it up. Let's give you a big hand.